These are your 5-3 notes on polynomial functions. We've been studying polynomials, adding, subtracting, multiplying, dividing them. Now we're going to look at what it looks like to graph them. And so lots of information today, a lot of new terminology. So the notes are a little long. I'm going to try to go quickly for you. Various different concepts, but not too difficult. So the first objective today is just to determine, is it a polynomial function in one variable? So it has to only have one variable. So in order to be a polynomial function in one variable, it has to only have one variable. When we go to graph these things, we have to have a relationship between x and y. So if you have x, y, and z, it doesn't work. So if you have more than one variable, it doesn't work. Don't be scared by crazy coefficients. The numbers out in front of the numbers can be real or imaginary. And the exponents of the variables must be non-negative. So non-negative, that's a stretch. Sometimes they're a little tricky when it's non-negative. So for number one here, looking at this, two variables, I have an x and a y. So not a polynomial function in one variable because there's more than one variable. More than one variable. Usually what they'll ask you to do is find some stuff about that function, if it is, and if it's not, tell me why it's not. 2 is good. Yep, it's a polynomial function. It just has a's, even though there's a power of a squared and then an a. It's yes, this one is. And number 3 is not. And the reason it's not is this n in the denominator. So you could say the variable's in the denominator. That really is 2 to the negative 1, 2n to the negative 1 power. So when the variable's in the denominator, it was a negative power. Another form of this, if you have a square root of a variable, that really means x to the 1/2 power, so that doesn't even have a power. So those are some of the problems that break the rules. All right, so the next concept is just some more terminology. Degree is the largest exponent of the variable. We've talked about finding the degree. Well, since there's only one variable, we won't have to add them up. It's the biggest one wins. The lead coefficient is the number out in front of the term that is the biggest one. And real zeros are where the graph crosses the x-axis. We already talked about real zeros in terms of a parabola. So a parabola can cross the x-axis twice, so those are the two real zeros. Okay, it could have the vertex on it, so that'd be one real zero. And we actually have the case where it doesn't touch it at all. And we said there were no real solutions, so there would be no real zeros. So we're just going to extend that to all the power functions. So we're going to be looking at not just squared. We already spent a whole chapter on things that are squared. We're going to be looking at everybody else, cubes, fourths, fifths, sixths. And so we're going to quickly go through some of the names and just what they might look like. These first two are linear. When you have a degree 0, though, a better way to name it is a constant. Degree 0, I'm just going to show you, it looks y equals 5. There is no variable. And what I mean by variable is the thing over here with the 5. The y is just telling you the relationship between that variable and the y coordinate. And so y equals 5 is a constant linear function. It is constantly 5. Doesn't matter what you plug in for an x value. It doesn't care. It doesn't have an x value. The answer is going to be 5. So 0, 5, 1, 5, 2, 5, negative 1, 5. So it's a horizontal line. It's constant. When you have a degree of 1, that means x to the first. So a function would be y equals maybe x or y equals 2x minus 3. So it can have a number after it. It can have a constant after it. It's not just the constant, but it has a variable, and then the constant or just the variable, it just depends. And then you could multiply the variable by something. It could be positive, could be negative, and that's called our slope. And these are linear. So the first one I showed you is the identity function. It just goes right to the middle on a 45. The second one I showed you there has a y-intercept of negative 3 and then has a slope of 2. So these are lines. They're going to cross the x-axis one time. Those are both functions found in Chapter 2. We're going to hit that chapter soon. kind of going backwards, going to do the really difficult things first, and then these other ones won't seem so difficult. Quadratics. This was our lovely chapter 4 that we just finished. We did everything quadratic. So degree 2, parent function is x squared, right? And that's just a parabola right at the origin, has one real solution. But now that we have a degree 2, all of the variables that could follow, we have combinations. We could have a linear term x and a constant 7. We could just have the x. We could just have the 7. So each time you raise it to another power, the more variation that can follow. And in chapter 4, we went through all the different things that those variations do. So another way, but these are all, they all look the same. So you can have a parabola looking upside down and shifted. It could be skinny, it could be wide, all sorts of different parabolas. 3 is a cubic, okay? When we cube something, raising it to the third power. So these are called cubic functions. A simple form of cubic would be y equals x cubed. And y equals x cubed kind of looks like an S going right through the origin. That's sort of your parent function. But again, because you're cubed, you could have x squared, x constant, any variation of those terms that follow. I could have the squared term and just a constant. I could have squared, x, all the way down. So each of those powers that follow, if they follow, each of those powers numbers out in front change the graph, and then the sign changes the graph. Is this going to get really big? Is it going to get really small? So it just depends on those combinations of signs, powers, and numbers. Another graph of the cubic, I'll just show you another one really quick. So another classic cubic would be something like this. So that's another way they look. So they're not all the same because there's more variation. We can't just say, oh, it's a parabola. There is no standard. There's different characteristics that we look for, but there's no standard anymore. Each time we raise the power, it just raises the variation. 4, for quarts in a gallon, we call it a quartic. Okay, y equals, again, now we have x to the 4th. We could have 4, 3, 2, 1, 9. We could have 4 squared. Doesn't matter. And so I'll just show you a quick little sketch of that. Kind of looks like a W. W's, or if it's upside down, like an M. But that's what some of them look like. Others kind of mimic more of a parabola. Not a parabola, but almost parabolic. So it just depends on what's going on with those powers. And the last one we're going to talk about is quintic. And they're bigger than this, but we named the first 5. So quintic, when you have quintuplets, that's 5 babies at once. So x to the 5th is a quintic. You could have 5, 4, 3, 2, 1, or any combination after that. And so what these look like each time, they just get a little bit more complex. And I think yep, I did okay there. So each time, they just get a little bit more like a roller coaster. I call these our roller coaster functions. So now what we're going to do is kind of break them down. We're going to break down, the rest of this chapter is all about graphing these things. So the whole goal at the end of this chapter, we're going to graph these things. So we're going to look at patterns. We're going to break these down step by step each day to get closer and closer to finally graphing them. All right, so some of the terminology here. If we have a degree, we're just going to give you a bunch of these polynomials. So this is a quintic. All right, so we can name it. This is a quintic. And its degree is 5 because that's the largest degree. And then you look at the number out in front of that degree and it's -3. So that's called the lead coefficient. The degree and the lead coefficient tells us a lot of information about our function. Number 2, the degree is 3. Even though it's in the middle of the polynomial there, we could rewrite that degree 3. So the lead coefficient, if we put it in order from the highest degree to the lowest, would be 5. And again, those things tell us bits and pieces about that graph. So that was degree 3. That's a cubic. And number 3, it has a degree 1 with a lead coefficient of 1. Okay, and the ones I'm talking about, here's the degree that's understood, and there's the one that's understood. And that is a linear function. That one's linear. And the last graph is just degree 6. We don't have a name for it. Degree 6, and that negative out in front is a -1 lead coefficient. So now that we understand degree and lead coefficient, we're going to look at the degrees and lead coefficients of different graphs and make some, look for some patterns to help us understand the graphs. So we're going to break the degree into evens and odds. Even degree functions do something different than the odd degrees. And then the lead coefficients we're going to break into positives and negatives. So on this next page here, if you look, lots of information here, but I'm just going to kind of break it down for you. These are both even degrees. So I'm going to say they're both quartics, probably. We don't have the equation. But based on what I'm looking at, the first graph is not a parabola. It's a little crazy towards where a vertex would be. And then the M, that classic M, is telling me that it's a quartic. There's some other things that could be telling me that as well. The positive, both arrows are going up, and the negative lead, both arrows are going down. So for instance, maybe, and I'm just suggesting maybe this is y equals positive 2x to the 4th, okay, and maybe this is y equals -3x to the 4th, and something else that ends up. But basically what we're saying is the number out in front, the lead coefficient, is positive for the first graph, negative for the second. We're going to describe the end behaviors of these graphs. So the end behavior, there's two end behaviors to these graphs. There's the left end behavior and the right. We're describing the arrowheads. So when we describe this arrowhead, because it's a function, it's always going out and to the left. And then the other arrowhead is always moving to the right. If they didn't go in opposite directions like that, it wouldn't be a function because they would cross over each other and they wouldn't pass the vertical line test. Okay, so this red arrowhead is moving up as it's moving to the left. And so we just get a little crazy with it because we're math people and that's how we talk. So instead of saying up and to the left, we're saying that the graph f of x is approaching positive infinity, and the x value is approaching negative infinity. So when you think about an ordered pair, the x coordinate is approaching negative infinity as the y coordinate is getting larger and approaching positive infinity. That's really what you're saying. So to describe that arrowhead, this is how it's going to look. F of x, the graph, approaches positive infinity as x approaches negative infinity. I'm going up and to the left. The smaller my x value gets, the higher my y value gets. That's basically what you're saying with that arrow. We're going to do the same thing with the green. So there's two end behaviors for each of these. So the green arrow is going up as it's going to the right, or it's approaching positive infinity as x approaches positive infinity. So f of x, the graph, the arrow is approaching positive infinity as the x values move to the right, go to the positive infinity. The y values are going up as the x values go up to the right. In the second graph here, the first arrowhead is pointing down. So that means f of x is approaching negative infinity as x approaches negative infinity because it's going down and also to the left. And the green arrowhead here is going down and to the right. So we just got to get fancy. F of x approaches negative infinity as x approaches positive infinity. I'm going down and to the right. So you have to have two end behaviors because there's two arrowheads. If you put the red after the green, that's fine. I think actually that's how the book does it. So if you ever check your answers in the back of the book, they describe the right arrowhead before the left. Seems backwards to me. That's why I do it this way, left to right. What you notice here is very similar to quadratics. If the number out in front, say the a value, right, the number out in front of the term, is positive, it goes both arrows up. And if it's negative, they're down, just like a parabola. And parabola is an even degree, so it kind of follows suit. So some of the summaries that I want to talk about here, write this down. These are our key elements here. Even degree polynomials They may not cross the x-axis. Think of a parabola, right? Not all of our parabolas had to cross the x-axis. Well, same thing with all these other crazy functions. All of their craziness can happen below the x-axis if they're facing down, or above the x-axis, and they never have to cross the x-axis. Even degree, if it's a positive lead, starts up, ends up, just like a quadratic. Negative lead, starts down, ends down. They're very even, so they both go the same direction, which is nice. And that's going to tell us a lot about when we have to graph. We'll look at the lead coefficient of the equation, we'll look at the degree, and that's going to tell us where our graph starts and stops. So this is the first part of figuring out how to graph these things. We'll know where the graph starts and where it ends based on the lead coefficient and the degree. All right, so now we're doing the same exact thing with the odds. We're going to take just a second to look at the graphs. So same idea. These are both odd degrees. Notice something else is different about them. They're odd looking. They're going in opposite directions. So I like to think of odd as opposite. Almost looks like ODD, looks like OPP. Right? They go in opposite directions. They're not even at all. The end behaviors are going opposite of each other. Now this is the tricky part. These right here. If it's a positive lead, I like to say it ends positive. Okay, and a negative lead, I like to say it ends negative or ends down. But when we say ends, we're talking about like riding the roller coaster. After the graph is finished, this first graph ends up. It ends in the positive, so it started down. If it has a negative lead, it's going to end, the ride is going to end down, so it started up. That is just going to be something you're going to have to memorize. Let's go ahead and do the end behaviors really quick. So I got a red arrowhead here. Okay, so it's going down and to the left. F of x approaches negative infinity as x approaches negative infinity. And then the green arrowhead up here, f of x is approaching positive infinity. It's getting bigger as x approaches positive infinity. As the x values get bigger, so do the y values. Okay, and then the next one here, one last time, and behavior for the red, f of x, arrow approaches positive infinity as x approaches negative infinity. That's the abbreviated form. Don't abbreviate it any more than that. The green arrowhead, f of x is approaching negative infinity as x is approaching positive infinity. So if you didn't understand that that's just saying up, down, left, right, it could be very confusing. And so it's nice to know this stuff. So when you see this, maybe on a standardized test or just anywhere else, you're not freaking out about them. There's one more in here somewhere. There it is. So a summary for our odd, they have to cross the x-axis. Think of a line. A line is going to go in opposite directions. So it doesn't matter which direction it's going. I know a horizontal might not cross, but that's a constant. So crosses the x-axis once. Okay, if they're odd, they're eventually going to cross. If it starts up and ends down, the only way you can do that is if you cross. It could cross multiple times, but it has to cross at least once. And this kind of just summarizes positive ends up. So it started down. Negative lead, it's going to end down, so it must start up because they got to be opposite. All right, so a little bit of all of this together now. We don't have the equations, we just have the pictures. I'm going to save you the time for the end behavior. We're not going to really do the end behavior part, but let's go ahead and do the odd and evens of these things. So this is an odd degree because it's going in opposite directions. Odd degree. We don't know what odd degree, if it's cubed, fifth, whatever, seventh power. And the fact that I ride the roller coaster and it's odd, they're going in opposite directions, and I end down means it's a negative lead. So the number out in front of the odd degree is negative, and it starts positive and ends negative. And then the real zeros, how many times it crosses the x-axis? There are 3 real zeros. Now, that doesn't mean that it's degree 3. That just means it has 3 real. It could have 2 imaginaries. We don't know. Okay, next graph is odd again, odd degree, because of the opposite motions there. It ends up, so that's a positive lead, and then it crosses 1 time, so it has 1 real 0. And number 3 here, because they both are facing the same exact way, they're both up, and they're both evenly facing the same way. This is an even degree. Because they're both facing up, that means the number out in front is a positive lead. We don't know what the number is, but we know it's positive. And it did not cross the x-axis at all, so we have no real zeros. All of our zeros here would be imaginary. All right, and the last thing we have to do is just review function notation. So it's been a while since we've done function notation. They're a little bit complicated. Take your time with these. As easy as they are, we make mistakes on our calculator. So when it says find f of 2, they're replacing the x value for the function in f of x function for 2. So basically they want you to calculate this when the x value is 2. So we write f of 2, the function evaluated for 2 is 2 cubed minus 2 times 2 squared plus 5 times 2 minus 7. Use parentheses, slow down, trust your mental math, and then maybe use your calculator. F of 2 equals 8 minus 8. 2 squared is 4 times 2 is 8 plus 10 minus 7. Now I would put it in my calculator because this kind of math is just annoying. 8 take away 8 is gone, 10 minus 7 is 3. What we're really saying here is that when you evaluate this function for 2, the answer is 3. On a graph, this ordered pair is on this function. The only other thing we know about this function, it has a positive lead, positive 1, odd degree. So that means it's going to be up and down. Okay? The fact that it's positive tells me it's going to end up and it's going to start down here somewhere. The only other thing we know right now, looking at it, is it has a y-intercept of -7. So maybe this graph starts down here, comes up, maybe comes down, we don't know. We don't know what happens, but we just know it starts down, ends up, hits the y-intercept at -7, and it goes through the ordered pair 2, 3. Okay, number 2 for the function g of x, different function, different letter out in front. That's just it's just a name, g of x. So g of x in terms of -3. Careful, the first negative is just the negative outside. You're multiplying this -3 to the 4th by a -1. Minus 5 times -3 squared plus 1. Big mistake is people think this negative here is this negative here, and that's incorrect. So using the order of operations, g of -3 is equal to -3 to the 4th is a positive 81, but then when I multiply by -1, I get a -81. -3 squared is a positive 9, but positive 9 times -5 is -45. And then add 1. G of -3 is equal to -126 plus 1. G of -3 is -125. Now, I'm not going to graph that, but really what they're saying is the ordered pair -3, -125 belongs on that graph. And it doesn't seem like it, but look what's happening to this number. We're raising it to the 4th power, which makes it really big, or in this case, really small, because it's going to be a negative of it. And then we square it and multiply it by -5, so it's going to get even smaller yet. So these graphs do some crazy roller coaster peaks and valleys because of all those powers. So your answer would just be this. I'm just kind of making the connection with the graph. All right, there you have it.